So now we want to introduce the idea of the binomial theorem. Okay? So a binomial, we say, is a polynomial with two terms that are joined by addition. So for example, x plus y, we'd say that's a binomial because the polynomial has multiple terms, two of them joined by addition. Okay? So would x plus x squared. Right? The difference between x plus y, actually I'd rather write in red. Difference between x plus y and x plus x squared, here there's two variables, here there's only one. Right? And so let's look at what happens when we expand out something like a plus b times c plus d. Right? The result, AC, AD, BC, and BD, is the result of multiplying every combination of one element in the first set and another element in the second set. Right? What does this remind you of? Cartesian product, right? Similar to Cartesian product. Okay? And so when we, instead of multiplying two different binomials, when we look at the case of multiplying or raising one binomial to some exponent, so in this case, the exponent 2, the result, again, will still be every combination of multiplying one element in the first and one element in the second. Right? So here, we have x plus y squared, which is x plus y times x plus y, which gives us xx, right? Xy, yx, and yy, right? Which combines to give us x squared plus 2xy plus y squared. Relatively straightforward, right? Cool. So we know we will have some number of x terms, or x's in our term, and some number of y's, right? And when we're choosing, one element from this parentheses and one element from this parentheses, we could either have two x's, right, which would result if we took an x from both of them. You could have one x and one y, right? Or we could have two y's. Is that clear? So any issues with that argument? In our result, we could either have two x's, one x and one y, or zero x's and two y's. Right? How many ways can we choose two x's and zero y's? Well, that's 2 choose 0. How many ways can we choose one x and one y? That's 2 choose 1. And how many ways can we choose 0 x's and 2 y's? 2 choose 2. It's the same as if I replace this with 2 choose 2, 2 choose 1, and 2 choose 0. Right? Because n choose k is the same as n choose n minus k. Choosing the number of x's to include in our product is the same as choosing the number of y's to disinclude in our product. Right? Any questions with that? So it tells me I have 2 choose 0 terms of the form x squared, 2 choose 1 terms of the form x times y, and 2 choose 2 terms of the form y squared. Right? And so I can rewrite the expansion as 2 choose 0 times x squared plus 2 choose 1 times xy plus 2 choose 2 times y squared. And this happens to be the exact same as what we saw above, right? 2 choose 0 is 1, 2 choose 1 is 2, and 2 choose 2 is 1. And again, if this wasn't clear before, the reason our, I don't want to say numerator, but the number we're choosing from is 2, is because we have two parentheses, right? Each term in our expansion will be the product of two terms, right? And they come from two potential parentheses. So if you want to generalize, each term in the expansion of x plus y to the exponent n will have k x's and n minus k y's. Right? This is similar to the argument we had with Vandermon's identity. If we have k x's, we'll have n minus k y's. Right? Because the total terms that we choose for each product will still be n. Right? Notice, oops, I didn't mean to show that, but in each term, the combined exponent of x and y is always 2. Right? Here it's x to the 2, y to the 0, the sum is 2. Here it's x to the 1, y to the 1, the sum is still 2. And here it's x to the 0, y to the 2, the sum is also 2. right? So each term will always be the product of two items. Or in the general case, each term will be the product of n items. And it's just a matter of how many different ways can we choose kx's and n minus ky's. Is this clear? Any issues with this? Okay, so then we can formalize the binomial theorem, stating that the expansion of x plus y to the exponent n looks like the sum, going from k is equal 0 to n, of n choose k times x to the exponent n minus k times y to the k. So if I want to write this out, I can say x plus y to the n looks like n choose 0, x to the k. I can write y to 0 if you want. N choose 1, x to the k minus 1 times y. N choose 2, x to the k minus 2, y squared, dot, dot, dot. Continue this expansion until x to the 1, y to the n minus 1, plus n choose n, y to the n. Right? And I could also write this sum as being n choose n minus k instead. Because remember, Pascal's triangle is symmetric, and n choose k is equal to n choose n minus k. So it's just a matter of how you want to interpret it. Do you want to choose the number of y's or choose the number of x's? Is that clear? So the interpretation we have right here, we're choosing the exponent on y. Is that clear? Any questions with this formalization? No? Okay. So as an example, let's expand whatever this is out. Okay? 3a squared minus 2b to the exponent 5. So if we're using the previous example, here we have x is equal to 3a squared and y is equal to negative 2b. Okay? So this expansion, 3a squared minus 2b to the exponent 5, would look something like 5 choose 0, 3a squared to the 5, plus 5 choose 1, 3a squared to the 4 times negative 2b, plus 5 choose 2, 3a squared to the 3, negative 2b squared, 5 choose 3, and so on and so forth, right? Right. There's only 2 more terms, but there's no need to expand. Is that clear? So here, don't always think of it as just being x plus y. X plus y are just placeholders for whatever else you substitute, whatever else you want to expand. Right. So here, x is 3a squared and y is negative 2b. And so that's how you'd expand that. Okay? Is expanding this out and doing all of the, multiplications you'd have to do, like right here, you'd have, 10 times 27 times negative 4. Like, is expanding that out to negative 1,080 important? Not really, but I think you should just try it out just once and get to a final expression, just to know that you can do it. Okay? So, like, this is just one step in the expansion. You would also, like, to be complete, you'd have to evaluate all the choosing terms, like 5 choose 0, 5 choose 1, blah, 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 and evaluate all the exponents as well. Is that clear? Any questions with all of this? Okay. So now here's an interesting question, and I want you to talk about it amongst yourselves for a second. What is the sum of the coefficients of the expansion of this quantity? And so it's 1, but let's take a look at why that's the case. Okay? So what's the first thought you might have when you look at this? Let's expand it up, right, and look at the coefficients. So why don't we do that? So this quantity, 3x squared minus 4x to the 12, will look something like 12 choose 0, 3x squared to the 12, plus 12 choose 1, 3x squared to the 11 times negative 4x plus blah, blah, blah. Right? I can do that and go from all the way from term 1 to term 13, right? Or you can think of it as term 0 to term 12. But that's definitely not what I wanted you to do, right? Did I expect you to sit there and evaluate 12 times 3 to the 11 by hand? No, right? So how do you think we could proceed? So we could common factor out an x, sure. But how would that help us towards getting our answer? So suppose we had let's suppose we had our expansion, right? Let me just make an example. Suppose we had some polynomial was equal to 4x squared plus 13. Why do we say this? Okay? How do I determine the sum of the coefficients here? Well, I just see 4, 13, and negative 17, right? I do the math and I get 0. But what numbers can I plug in for x and y to also give me the same result? One, right? If I substituted in 1 and 1, it would get rid of the influence of the x and y terms, and I would be left with just the sum of the coefficients, right? Here I would get 4 times 1 plus 13 times 1 times 1 minus 17 times 1, which gives me 4 plus 13 minus 17 exactly as I want, right? In this case, that gives me 0. Is that clear? So if we have some expression and we substitute in 1 for all of the variables, it will give us just the sum of the coefficients. Okay, so how can we extend that to our case? Well, we just substitute x is equal to 1, right? Right, and what does that give us? 3 times 1 minus 4 times 1 to the 12 is negative 1 to the 12, which is 1. Is that clear? Right? And so now, what if I wanted to ask the general question, what's the sum of the coefficients of 3x squared minus 4x to the exponent n, right? It would either be 1 or negative 1 depending on n, right? And I think that's kind of interesting because suppose we had 3x squared minus 4x to the 1,000, right? So those numbers would be of the form, I don't know, 1,000 choose 3, 3x squared to the 997. Like those are massive numbers. But the sum of the coefficients would still be either 1 or negative, which I think is pretty interesting. Does everyone sort of see what I'm trying to say? Cool. Cool. So to find the sum of the coefficients, we let all the variables be 1, and it sort of falls out on its own. Sound good? Cool. So now I want to introduce this idea of the general term, okay? And we'll probably be able to see the benefits of this more next week, unless I'm able to finish it today. So we define the kth term in the binomial expansion as n choose k times x to the exponent n minus k times y to the k. So it's just a compact way of referring to the kth term. And k could go from 0 to n. So we're assuming that that very first term is term 0. Like that's just how we'll number it. We'll 0 index it, right? So we have term 0, term 1, term 2, all the way until term n, right? Which makes sense because now our expansion has n plus 1 terms, right? That's familiar because in the Pascal's triangle, the nth row had n plus 1 terms. Right? These are just the numbers from Pascal's triangle. Okay? So if we wanted to calculate the general term of 3a squared minus 5b to the exponent 5, we would do exactly that, right? Instead of n choose k, we'd have 5 choose k. We have 3a squared to the exponent 5 minus k, and negative 2b to the exponent k. So one of the things we always do in the general term is isolate that power of negative 1 if it exists, and put that to the front, because it makes it immediately evident whether or not that term is positive or negative, right, depending on the value of k, right? Then we have 5 choose k, and what I like to do is separate the exponential bases, right? So here I have 2 to the k and 3 to the 5 minus k, okay? And I like writing it like this as opposed to negative 2 to the k, because this separates determining whether or not the number is positive or negative and the numbers themselves, right? And then here I have my exponent on a to the 10 minus 2k, and b to the k. Okay? So this tells me at a glance, right? And what I can do is, suppose I want to know the exponent on a and b in the third term, I could just plug in k is equal to 3 and get that entire term right away. And more specifically, if I want to know, what the exponents on a and b will be, I could plug in 3 into 10 minus 2k and get 4, and plug in 3 for k and get 3. So I get, for term 3, it would be something times a to the 4, b to the 3. And I can identify that very easily without having to write out the expansion. Is that clear? Right. Or if I want to determine the coefficient on the fourth term, I don't have to go and expand out the entire thing. I could just plug in k is equal to 4 for that part. Right? And that would give me the coefficient of the fourth term. Is all of this clear? So this is the general term. Okay? So I want you to work on an example. Find out the general term of x to the 5 minus 1 over x squared to the exponent 7. Okay? Of course, you can write this as x to the 5 minus x to the negative 2. Let's walk through it, right? So tk will be 7 choose k times whatever the first argument is, in our case x to the 5, exponent 7 minus k, times negative x to the negative 2 to the k. Is that clear? Right. The first step I want to do is isolate that negative 1 to the exponent k term. So it'll be out front so I can tell which terms will be positive or negative. Right. Then I have 7 to the exponent k. Then here I have x to the 35 minus 5k. Is that clear? That comes from that expansion. And then from this last part, I get x to the negative 2k. Okay? So this is almost like a special case because both of these variables, my x and y, were both in terms of the same variable x, right? If this was x to the 5 minus y to the negative 2, I would be done here, right? But since both of them involve an x, I can combine them into negative 1 to the k, 7 choose k, x to the 35 minus 7k. Is that clear? So now, quickly and concisely, if I want to determine a specific term, I just plug in a value of k and that gives it to me. Is that clear? Any questions with that? Okay. So now I want to look at an example use case of this. Okay. Let's take a look. So again, we had negative 1 to the k, 7 choose k, x to the 35 minus 7k. So one potential question I could ask is, what's the term, or what's the coefficient of the term where it looks like x to the 14? So what's the coefficient on x to the 14? How could I figure that out? Coefficient on x to the 14. How would I find that? Yeah.
You first solve 35 minus 17 equals 14 and then put that value.
Yeah, I can solve 35 minus 7k is equal to 14. I believe it gives you k is equal to 3. Right? And then you could find whatever t sub k is. Or t sub 3 is. Is that clear? Okay. What if I wanted to find the coefficient on x to the 30? Then what? Yeah.
It's not possible.
Why not?
Oh, it's 0.
Sure. I mean, I'd rather go with the first option, that there is no coefficient on x to the 30, right? I guess saying that it's 0 is another way of saying that. But here, we know if we set the exponent, 35 minus 7k equal to 30, you get that k is equal to 5/7. But that's not possible because here, k was our index for what term we're looking at, right? K was an integer between 0 and n inclusive. So here it doesn't make sense for k to be a non-integer. Is that clear? So any questions with that? Okay, so the last thing I wanted to look at was, suppose I had two expansions, right? So I have, like, I don't know, f of xy is equal to 3x minus y squared to the 7. G of xy is equal to 4x squared minus 3y to the 8. What's the general term of expansion of f of xy times g of xy? Right? And so what I would have to do in that case, we won't work it out today. We can continue this next week or in discussion on Monday. But what you can do in that case is compute the individual general terms of f and of g, multiply them together, and your general term will be of the form t of, like, I don't know, k comma j. Is that clear? So again, we won't work that out right now. And the last sort of extension of this idea is, what if we're looking at, instead of a binomial, we look at a trinomial. So pretend we have 3x minus 4y plus 3x squared y. There's too much similarity there. Why do we do 14y squared to the 7? Okay, so there we're looking at trinomials instead of binomials. Okay? So how do we extend this? Any ideas? Pardon? Okay, so one initial idea is to pretend that is one term, and then we just pretend that's box. Then we're just looking at the expansion of box plus 14y squared to the 7. You can definitely do that, but then for each of those 8 terms, you'll have to do the expansion of whatever's in the box. So you'll have like a nested binomial expansion. So that gets a little messy. So you can actually extend binomials theorem to trinomials and, in general, multinomials, okay? But we'll talk about that more next week. Okay, so I think I'll end a little early today. So that's it. If you have 61B or E16A this week, good luck. And homework should be out by tomorrow. And we'll see you in discussion on Monday.